Hello, good afternoon, dear attendees of the International Congress of Materials. My name is Erik URIBE, and I'm going to present my work entitled as Enhance the Fluoride Absorption in Hkust 1 by Functionalized with Amino Acids. Starting with the introduction part, fluorine is an element of high electronegativity of great abundance on Earth. Periodically, it is associated with other cations and can form ion fluorides in rocks. The fluoride mineral with the largest amount of the planet is fluorspar. It is a composed of calcium fluoride and apatite. It is usually composed of carbonates, sulfates, fluoride, and calcium. Fluoride is one of the most abundant natural contaminants in water intended for human use and intake, with the greatest distribution in the world. Fluoride contamination of water occurs naturally in the subsoil, although its concentration is increased due to the overexploitation of aquifers. The concentration can be affected by the class of minerals in which it is associated, its porosity, soil acidity, temperature, etc. The presence of fluoride is common in Asian countries such as Taiwan and China, in America in Argentina, Chile, and the United States. In Mexico, these conditions are especially presented in states such as Durango, San Luis Potosí, and Jalisco. In this state, fluoride contamination represents a serious public health problem. The fluoride content present in underwater is due to natural sources such as leaching from rocks and minerals. Water with a low concentration of fluoride has a beneficial role in human health for bone formation and prevention of dental caries. However, a high concentration of this ion can lead to dental or skeletal fluorosis. The main source of fluoride intake is drinking water because of the World Health Organization established the permitted limit of fluoride concentration in drinking water to be 1.5 milligrams per liter. The fluoration allows the concentration of fluoride in aqueous effluents to be reduced. The most commonly used methods for fluoride removal are precipitation, absorption, ion exchange, nanofiltration, etc. However, most of these techniques are difficult to apply and very expensive. Among the above techniques, the absorption technique has received the greatest attention due to its low cost, simplicity, easy operation, efficiency, and rapid response time. It is because of this that it has been widely used for water defloration, providing a safe level of fluoride for consumption and use. MOF have aroused great scientific interest in absorption applications due to their permanent porosity, large surface area, and controllable pore size in both microporous and mesoporous domains. Their remarkable absorption properties have enabled to the use of MOF in a wide variety of different applications such as gas absorption and storage, heterogeneous catalysis, and sensing. Recently, MOF have also been explored as new platform for the absorptive removal of contaminants from aqueous media. Hkust1 is formed by dimeric metallic copper units which are connected by benzene 1,3,5 tricarboxylate acid linker molecules. This MOF has attracted much attention due to its high surface area, can be synthesized with commercially available reagents, and possesses accessibility to coordinately unsaturated sites. However, Hkust1 has a low stability in water. It is due to this that in the present work proposed its post-synthesis functionalization with amino acids to increase its stability and evaluate its fluoride absorption capacity. The hypothesis and objectives of this work: Hkust1 functionalized with different amino acids will have higher amount of absorption sites, different porosity, and thus increase the stability and absorption capacity of fluoride ions in water. The general objective of this work is to be absorbed fluoride on the copper metalorganic network Hkust functionalized with amino acids. Regarding the part of the methodology followed for this work, the synthesis of Hkust was performed by previously reported procedure as a solution was prepared with 2 millimole of organic ligand 1,3,5-diphenyl tricarboxylate acid and 80 milliliters of deionized water, stirred until complete dissolution. In a second solution, 3 millimole of copper nitrate and 100 milliliters of ethanol were added. Once the second solution was dissolved, it was added dropwise to the first solution and the mixture was kept stirred for 24 hours until a blue solid was formed. Subsequently, the mixture has placed in centrifuge tubes. Once the components were separated, the solid was dried in an oven at 70 Celsius rates for 4 hours. The solid obtained was stored for storage, and the solid obtained was stored for further characterization. The functionalization methodology was performed in a posynthesis process as reported by Returani, where 0.3 grams of Hkust was put in contact with a dilution of each amino acid. Additionally, each dilution contained dissolved sodium hydroxide to aid the proper dissolution of all amino acids employed. The mixture was agitated at room temperature for 24 hours. After this time, the solid was separated from the liquid by centrifugation at 600 rpm for 30 minutes. Okay, regarding the results obtained in this research work, the following are the most important ones. The study of the structure of the MOF obtained was carried out by means of X-ray diffraction. Figure 1 shows the index diffraction pattern for the synthesized material by styrene at room temperature, in which can be clearly observed that the diffraction planes have definition and belong to the cubic structure reported for Hkust. The crystal size corresponds to a nanoscale material of 30.54 nanometers with a lattice parameter of 26 angstroms. Figure 2 shows the diffraction patterns obtained for the Hkust samples functionalized with the amino acids proline, tyrosine, cysteine, and serine with a 36 weight percent. It can be seen that the diffraction patterns possess the same reflections characteristics of Hkust, which means that the MOF structure is preserved after the functionalization with the amino acids. The crystal size D of the functionalized MOF corresponds to nanometer scale materials between 29 and 33 nanometers. It was observed that D increased with the amount of the amino acids for most of the samples obtained, being the largest crystals of the functionalized samples with 36 weight percent. Figure 3 shows the FTIR spectra obtained for pristine Hkust and for the samples functionalized with 36 weight percent of amino acids. It was possible to determine that the bands related to the hydroxyl vibrations around 30,250 centimeters are related to the water or ethanol molecules present in the MOF. The characteristic bands of copper BTC crystals are mainly concentrated in the range of 500 and 1,800 centimeters. In the table 1, the results obtained for the absorption capacity for pristine Hkust and 36 weight% amino acid functionalized MOF samples are presented. The pristine Hkust succeeded in removing fluoride by adsorbing 0.28 milligrams per gram without any additional functionalization. On the other hand, amino acid functionalized MOF also managed to adsorb fluoride from the prepared solution to a greater or lesser extent, being the MOF functionalized with 36% of serine, the one that achieved the highest absorption capacity in up to 0.71 milligrams per gram. This could be attributed to the fact that observing its corresponding diffraction patterns, the Hkust network structure is well preserved by observing the characteristic reflections of Cooper MOF and to the reactive functional groups possessed by this amino acid. Finally, as conclusions of this research project, it was verified that by posynthesis functionalization of amino acids, the structure of Hkust was maintained by observing the characteristic reflections of the MOF. The obtaining of the desired materials was also corroborated by FTIR by observing in the pristine Hkust the bands associated to the characteristic peaks of Cooper BTC crystals are mainly concentrated in the range of 500 and 1,800 centimeters. As for fluoride absorption, the contaminant was successfully removed from the solution prepared with 11 parts per million of fluoride of potassium using pristine Hkust managing to remove up to 0.28 milligrams per gram. All the samples functionalized with the amino acids managed to remove fluorine, obtain different absorption capacities between 0.14 and 0.71 milligrams per gram, paying them off with the highest absorption capacity, the one functionalized with the 36 weight% of serine, because this amino acid has 4 reactive functional groups which may have van der Waals interactions present between the functional groups of the amino acids present in its structure and the contaminating fluoride in the solution. In order to improve the absorption capacity of Hkust, it is proposed to use in a functionalization an amino acid with a higher amount of functional groups and to evaluate its fluoride absorption capacity. Well, thank you very much for your attention. If you have any questions, I have attended in the chat or in the application. Have a nice day. Thank you.